Hello, my name is Andrew, and this is my collisions lab for Physics 2211. For this lab, there's one pool ball that was struck by a pole cue stick and collided with another pool ball. I used tracker software to determine the position of each ball. I used a computational model to test the same experiment. The purpose is to analyze the effect collision has on motion and to test the conservation of momentum, as well as the conservation of energy. The purpose is also to compare the computational model to the actual observed motion. The main result was that there was a 0.0136 kilogram meters per second loss in the magnitude of momentum, so the momentum was mostly conserved, while there was a 33% loss in the kinetic energy. I used the position and velocity update formulas, which are derived from Newton's second law. I also used the kinetic energy formula and the energy principle, that the change of energy in a system is equal to the change in energy of all the components of energy, which in this case, it's just kinetic energy, which is equal to 0. The momentum principle, that momentum equals mass times velocity, and the conservation of momentum, that the sum of the initial momentums of each mass equals the sum of the final momentums of the same masses after a collision. I found online that the average mass of a pool ball is 0.163 kilograms, which is the value I chose to use. The position of the yellow ball was 0.003 for the x component and negative 0.007, which is basically on the origin. For the blue ball, negative 0.51 for the x and 0.006 for the y, which is basically just half a meter left of the origin. The velocity of the yellow ball once it's hit by the pool stick is negative 0.505 for the x and 0.0035 for the y, and the blue ball is at rest. The system is a yellow and blue balls, and the surroundings are the earth, air, and pool stick. On the right, we can see that at first only the yellow ball has momentum that goes directly left, while after the collision, the blue ball has momentum to the left and downwards, while the yellow ball has momentum up and to the left. I recorded this video in slow motion so it would have more frames per second. The yellow ball moves along the x-axis. Most of the momentum is transferred to the blue ball, causing the yellow ball to slow down and the blue ball to speed up. The yellow ball moves so slowly that it was difficult to accurately place the center of mass at each frame. The collision occurs at 1.067 seconds, which we can see from where the graphs change their slope. The yellow ball has a slower x and y velocity after the collision than the blue ball does. However, the y velocities are similar. For my code, I first created two objects using this code here. Then I created the graphs for the x and y positions here. I gave the mass in kilograms and used the position given by the tracker here. I determined the initial velocity of the yellow ball by creating a linear trend line in Excel using the first few points after the ball is struck by the pool stick. The blue ball, of course, is at rest before the collision happens. This code is to calculate the momentum and energy before the collision happens, which happens at time equals 1.066 seconds. I used the velocity update formula here and the position update formula here. This code provided the initial momentum and the initial kinetic energy of the system. This code right here in specific uses the left half of the conservation of momentum principle with the initial velocities, and this code here is a kinetic energy formula. I determined the velocities after the collision using the same trend line method in Excel, using the first few points for the blue ball and yellow ball to determine their new velocity. I used the same formulas as before the collision, but made it so that it was for when time was less than 3.733, which is when the video ended. These calculations gave me the final momentum and the final kinetic energy. In the x position graph, the yellow ball is barely moving, while the blue ball is moving quickly. They have similar but opposite motion in the y position graph, however. This model shows motion very similar to the video. The observed and computational data differ after the collision. This is because the computational slope is based on the first few points of motion, which is when the velocity is the highest, because it's before friction acts on it and slows the ball down. The same thing is occurring here. The slope becomes less steep in the observed data due to friction, while the computational model doesn't account for friction. It maintains the slope of velocity right after the collision. Some sources of error is that I used the velocity of the yellow ball right after the pool stick struck the ball, rather than using the velocity leading up to the collision. The ball had time to slow down before the collision due to the friction and air resistance. The initial momentum didn't equal the final momentum due to this. Also, the yellow ball moved very slowly after the collision, making it difficult to perfectly track the center of mass from frame to frame. This led to some inaccuracies in determining the final velocity of the yellow ball. The initial momentum was negative 0.082 for the x component, 5.705 times 10 to the 4th kilograms meters per second, while the final momentum was negative 0.069 for the x, negative 2.77 times 10 to the 4th kilograms meters per second. These are similar vectors, but they're not equal. The magnitude of the initial momentum was 0.0823 kilogram meters per second, which was greater than the final momentum, 0.068. 7 kilograms meters per second. That was a 0.0136 difference. There was a loss of velocity from when the pool stick struck the yellow ball to when that ball collided with the blue ball, which caused a lower final momentum. Rotational kinetic energy was not accounted for in this lab, so translational kinetic energy is only kinetic energy at play here. The initial translational kinetic energy was 0.0208 joules, while the final was 0.139 joules. The kinetic energy was not conserved. There was a loss of 0.0069 joules, which is about 33% of the initial kinetic energy. This is again due to friction. Since there was a loss in kinetic energy, this means that it was an inelastic collision. This is expected because real-life collisions are rarely ever perfectly elastic. Also, some of the translational kinetic energy may have become rotational kinetic energy, which the computational model would not have accounted for. Thank you for watching my lab.